Okay, so hello, welcome to Math 2000 Lab 3. Unfortunately, the video from lecture today did not record the document viewer, so I will be remaking this lab using my whiteboard here. So let's go ahead and get started. Share. Okay. So in this lab, we'll be doing different proofs using sets. And so let's just go ahead and get started with exercise 1. It might help if I plug in my pen. Okay, so exercise 1. So we are going to be prove the associativity identity for sets, which is A union B union C with the brackets as such is equivalent to A union B union C. Okay, because we want to prove that these two sets are equivalent, we have to prove both ways. So to prove this, we must show 1, that A union B union C is a subset of A union B union C. And secondly, we must show that A union B union C is a subset of A union B union C. Okay. So if this is a subset of this, and this is a subset of this, then obviously they are equal. So part 1, we are showing this right here. So assume X is an element of A union B union C. If this is the case, then this is equivalent to showing that X is an element of A, or X is an element of B union C. Okay, and we'll keep going down this proof. So this is equivalent to X is an element of A, or if X is an element of B union C, then that's the same as saying X is an element of B or X is an element of C. And so now we can use our associativity law with respect to or and get rid of these brackets. So we have X is an element of A, or X is an element of B, or X is an element of C. Okay, and so now we want to, from here, construct the A union B union C. And so we can move the brackets around to X is an element of A, or X is an element of B in brackets, or X is an element of C. And now we're going in the reverse direction. We're going from ors and X as an element to individual elements back to using unions. So this is equivalent to X is an element of A union B, or X is an element of C, which is equivalent to X is an element of A union B, or X is an element of C. And lastly, that means that if X is in this sets, this union, or X is in C, then that's the same as saying, or equivalent to saying, X is an element of A union B union C. And therefore, A union B union C is a subset of A union B union C. And so we've shown part one. And now we do a very similar thing to prove part two. So part two, we want to show, so first we want to show, if we move up here, we want to show that A union B union C is a subset of A union B, is A union B union C. So we will assume that X is an element of A union B union C, which is equivalent to saying that X is an element of A union B, or X is an element of C. And we can then break up this A union B, and we get X is an element of A, or X is an element of B, or X is an element of C. And now we can use our associativity rule with respect to ORs, and we get X is an element of A, or X is an element of B, or X is an element of C. And from there, we can rearrange the brackets, or add brackets rather, to the second two terms. So X is an element of A, or X is an element of B, or X is an element of C. And this is equivalent to saying that X is an element of A, or now X is an element of B union C. And then we will now combine all of this. So if X is in A or X is in B union C, then obviously X is an element of A union B union C. And this is the same as showing that therefore A union B union C is a subset of A union B union C. And so now we've proven part two. And so because we've shown both part one and part two, we can therefore say that A union B union C is equivalent to A union B union C. And that's what we wanted to show. So that is the first exercise. Okay, and we'll move on to exercise 2. Okay, now we're going to prove the transitive property. So what is that? So prove the transitive property. And that is to say that if A is a subset of B and B is a subset of C, then A is a subset of C. Okay, and this makes logical sense, right? So if all the elements of A are definitely in B and all the elements of B are definitely in C, then it's logical to say that all the elements of A are obviously in C. But just because it's obvious doesn't mean we don't need to prove it. So first we will assume that A is a subset of B and that B is a subset of C. And if we assume that, and we let X be an element of A, let X be an element of A be true, then we use this idea right here that we know to be true. We know that A is a subset of B. We've assumed it. And A is a subset of B is equivalent to saying that if X is an element of A, then X is an element of B. So because of this, we know, thus, X is an element of B. Because we know it's an element of A, we've assumed that, let it be in there, then we know X is also an element of B. Okay, is true. And so now we use what we've assumed as well, that B is a subset of C. And we say that B is a subset of C is equivalent to saying if X is an element of B, then X is an element of C. Thus, for all X, if X is an element of A, then X is also an element of C. So every element that's in A is also in C. And what does that mean? Well, by our definition of subset, therefore, A is a subset of C. And overall, we've just shown that if A is a subset of B and B is a subset of C, then A is a subset of C. And that is the proof for exercise 2. And so we'll move on to exercise 3. So in exercise 3, we have a little bit of a different question. So let A equal the set of N such that N is equal to 4K plus 1 for some K is an element of integers, or Z. And we will let B equal to the set of N such that N is equal to 4K minus 3 for some K is an element of Z. Okay, so we have that, and we want to prove that A is equivalent to B. Prove that all the elements in A are also elements in B, and all the elements in B are also elements in A. So they're equivalent. So since we're proving equivalence, we once again, to prove, we must show two things. One, that A is a subset of B, and two, that B is a subset of A. Okay, so to show that, part 1, A is a subset of B. So first, let X be an element of A. By definition, X is equal to 4I plus 1. And I've changed the value I just so that we don't get confused with the other variables for some I in Z. And what do we want to do? Well, we want to show that this number X from A to be a number in B. So if we can show that this number X from A is also in B, and this X is any X, so any value that is within A, then we've shown that every element in A is also in B. So essentially, we want to show that 4i plus 1 is equal to 4j minus 3. And j minus 3 is from the second set here. Just replacing k with j. Okay, well, what is basically we need to find, okay, how do we get from this number here and prove that this number is equal to this number? Well, we're just going to pause here for a moment and do a quick aside. So recall that A is n such that n is equal to 4k plus 1. And we have the requirements there. And B is equal to n is equal to 4k minus 3. Okay, so if let's say k is equal to 1, then n would be 4 times 1 plus 1, which equals 5. If k is equal to 2, n is equal to 4 times 2 plus 1, which is 9. And if k is equal to 3, then n is equal to 4 times 3 plus 1, which is equal to 13. And in B, if k is equal to 1, then n is equal to 4 times 1 minus 3, which is equal to 1. If k is equal to 2, then n is equal to 4 times 2 minus 3, which is equal to 5. And if k is equal to 3, n is equal to 4 times 3 minus 3, which is equal to 9. And so what we see here is that this 5 relates to this 5, this 9 relates to this 9, and this pattern would continue. But how can we use this to determine what we need to sub in to J in order to get 4i plus 1? Well, if we have here, this number here, so 5 comes from k equals 2, and this 5 comes from k equals 1. So if we sub in j is equal to I plus 1, then we should get them to be equal. So let j equal to I plus 1. If that's the case, we have 4j minus 3, which is equal to 4i plus 1 minus 3, which is equal to 4i plus 4 minus 3, which is equal to 4i plus 1, which is equal to the number x. So what we've just shown is the number 4j plus 3 from B is equal to the number from A, which is both x. So we've just shown that for any x, if it's in A, well, it is from A, then it's also in B. Thus, let's write this down. X is equal to 4j minus 3 for some j, which is an element of Z. And more specifically, j is equal to I plus 1. Thus, X is an element of B, and therefore A is a subset of B. So we've proven part one. And now we have to prove the opposite. It's going to look very similar, but let's get to it. Pitter patter, let's get at her. Part two, B is a subset of A. So let X be an element of B. By definition, X is equal to 4i minus 3 for some I, which is an element of Z. We want to show that this number, X, from B is equal to a number in A. So essentially, we want to show that 4i minus 3 is equal to 4j plus 1. And we're going to use the same idea that we had back here, except we're going the opposite direction. So we're in B, and we have, for k equals 2, we get 5, but it's one value less is what gets us 5 from A. So instead of adding 1, we will subtract 1. So let j equal to I minus 1. So we have 4j plus 1 is equal to 4i minus 1 plus 1, which is equal to 4i minus 4 plus 1, which is equal to 4i minus 3, which is equal to x. So what we've just shown is that given some number from B, 4i minus 3, that it is equal to a different number, or that it is equal to x, and that number is also in A, as right here. So this number from B is also in A. And so what we've essentially shown, thus, x is equal to 4i minus 3 for some I, which is an element of Z. I is equal to j minus 1, or sorry, or this is j, for j minus 3 for some j, where j is equal to I minus 1. Thus, x is an element of A, and therefore B is a subset of A. And what we've just shown by showing both part A and part B is that A is equivalent to B. Okay, moving on, we will do exercise 4. Exercise 4 states, prove the following. If B is a subset of C, then A cross B is a subset of A cross C. Okay, so what's this saying? Is that B is a subset of C, so everything in B is in C, And that means that A, every item in A paired with every item in B, that's what cross means, is a subset of every item in A crossed with every item in C. So let's just write that out formally. Recall that A cross B is equal to the set of A, B pairs such that A is an element of A and B is an element of B. Okay, so recall, this is A cross B is the set of pairs where A is from A and B is from B. And so we'll let XY be an element of A cross B. And so basically what we want to show is that if XY is an A cross B, that it's also an A cross C. So how are we going to do that? Well, if this is the case, then X is an element of A and Y is an element of B. We know this by definition. We also know that B is a subset of C, which is equivalent to saying that if N is an element of B, it implies that N is an element of C. So everything in B is also in C. And that means that since Y is in B, that means that Y is an element of C. And therefore, XY is an element of A cross C. Because A cross C is a pair of every element in A paired with every element in C, and X is in A and Y is in C, we know that XY is going to be in A cross C. So therefore, we can say that if B is a subset of C, then A cross B is a subset of A cross C. And that's our proof. And we have one final example that we're going to do now. Okay, exercise 5. Prove the following. We have a set P. We have a set where P of P's such that P is a prime number. And we intersect that with the set where K squared minus 1 such that K is an element of the natural numbers. And what we want to say is that this intersection only contains the element 3. So of all the prime numbers and all the numbers following this format, the only number that is within both sets is the number 3. So let's go ahead and prove that, okay? Let X be an element of P such that P is a prime number. Intersected with K squared minus 1 such that K is an element of the natural numbers. Okay, so X is an element that's in this intersection. We want to prove that that X has to be 3. There's no other options. So this means that that X is a prime number and that X is equal to K squared minus 1 is equal to k minus 1, k plus 1. Okay. So what does this mean? This means x has two factors, which is k minus 1 and k plus 1. And as an aside, we also know, that every prime number has two factors, 1 and itself. That is by definition of prime numbers. So if we combine these two facts, that x has two factors, x minus 1 and x plus 1, and x, which is a prime number, has two factors, 1 in itself, that means one of these has to be 1. Okay, but so let's just go ahead and see. Okay, is it k plus 1? Can k plus 1 equal 1? It can't, because k is from the natural numbers, and the natural numbers does not contain the number 0. The only number that works, 0 plus 1 equals 1, is not possible. So no, it's not from there. So that means we know k minus 1 equal 1. Well, if we do some very easy algebra, we find that k is equal to 2. And we're getting close to being done. If k has to equal 2, thus x, which is equal to k minus 1, k plus 1, we sub in 2, we get 2 minus 1, 2 plus 1, which equals 1 times 3, which equals 3. What we've just shown is that x has to equal 3. It's the only possible option, because the only possible option for k is 2. So this is the only element. This is the only element. And we will write out our concluding statement. Therefore, P, the set of P, where P is a prime number, intersected with k squared minus 1, such that k is an element of the natural numbers, is equal to the set containing 3 and Q, E, D. Okay, that was your third lab solutions to the problems. This will be posted on CourseLink, as well as the document that I made. And this was my last week running the lab. You will have 2 other TAs, one for the next 4-week section and one for the one after that. It's been a pleasure, and I hope you all have a great rest of your week. Thank you. Well, let's find where to stop recording.